we can solve for area exactly whenever the boundaries of any of the shapes or any of the integration bounded areas, I should say, I guess, area between the function and the horizontal axis, between a left bound and a right bound for any definite integral. When the boundaries are linear or circular, we're good. Geometry, done. But whenever the boundaries are not circular, aka whenever the graph has a curve that is not linear, which is not really curved, or circular, then we have to use left, right, midpoint, and who was T? And that's what we were wrong way. That's what we were starting to talk about yesterday. We did not get to fill in the blanks. At the very, very top, trapezoidal approximations are one of the better. Oh, sorry. I need to remember that my computer is not happy today, and I am doing a workaround. Okay, one of the, there we go, better approximation techniques. One of the better approximation techniques. Midpoint is pretty good. Trapezoidal is pretty good. It truly doesn't matter which approximation we're using if we're taking the limit as the number of rectangles approach infinity, which is better stated the number as the partition or the bases of the rectangles are approaching 0, because the more you fit in, the thinner they get. It's a better way of putting it, a more precise way of putting it. So in the long run, in order to solve for the exact area, it doesn't really matter which one you use. But in the short run, or, remember how I told you guys there are some integrals that can't actually be integrated?
Yes.
So if there are some integrals that can't actually be integrated, that means that they can't be found precisely. They have to be found approximately. However, these approximation techniques can be more and more accurate as we fit in more and more. So it could be, I guess you could say, it could get to where the error is negligible, or where it gets ultimately close enough for the, I don't know, for the number that we need, for the quantity that we need to find, etc. But if, once again, if some integrals cannot be integrated, if some antiderivatives cannot be found, the only way to actually solve would be with approximation techniques. That's why they're kind of important. But the trapezoidal one, we pretty much finished yesterday. We were actually like 5 minutes ahead of period 1, which turned into like half a class period ahead of period 1. So it took us like half a class period to figure out this example and be able to do it on the board. We were able to talk about how for the area formula of a trapezoid, bases are still going to be our delta x's, are still going to be the change in the x's. The heights are going to come from the function values. We're going to use both of them at 0 and 1, at 1 and 2, at 2 and 3 for every single area, because a trapezoid uses 2 heights, not just 1. What we didn't do, though, is finish. So, kiddos, let's finish this example so we have it all nice and neat and solved. How do we finish this puppy out?
Plug in.
Plug in what?
The function is 9 minus x squared.
Good. So the function is 9 minus x squared. All we have to do is say, okay, we have 1/2 times 1 of, who is f of 0? 9 plus 2 times who is f of 1?
5. Oh, wait, no, wait, sorry,
8. 8 times 2 is 16, plus 2 times f of 2. 5 times 2 is 10, and then who is f of 3?
0.
0. Remember, just plug it in. You guys do this math better than I did this morning. Add 9 plus 16 plus 10?
35.
Nice. I said 37 and no one caught me for like a full 3 minutes. Anyway, 1/2. Actually, they didn't catch me. I caught myself. Struggle. Which would be 17.5. 17.5 or 17.5, and that would be our trapezoidal approximation. Kiddos, why does it make sense? Do you guys remember, this was the example from section 4.2. Do you remember what the actual area was? The actual area, 4.2. The actual integral from 0 to 3 of 9 minus x squared. Ooh, calculator's out. How do we solve actual definite integrals using a calculator? It's kind of cheap right now, but it's okay. It shows us the exact answer. Nope, you don't even need to know the summation. Wait, I need the area under a function in between integral. Math. Go to the math menu, go find me the integral. Or you can do second window. Is that where the function integrate shortcut is? You can do second window. Sorry, alpha window or math, and go down. Finding function, integrate. Remember, when we're finding the area between a function and the horizontal from a left bound to a right bound, When we're approximating the definite integral. So this is the guy that you want to plug into your graphing calculator. The definite integral from 0 to 3 of 9 minus x squared equals, what does your calculator say? 18. 18. Why does it make sense from the picture that this would be a little bit below, but close to 18?
Because it cuts off the function.
Yeah, it cuts and then some of the curvature is going to be over, so it's going to be an under approximate. Now, hold on. Go back and look at 4.2. Look at the left-hand approximation, which was also, no, that was over. Look at the right-hand approximation, which was also under. Because when you would hit at the right and come back, there would be all that curvature missing. Hit at the right and come back, all that curvature missing for any decreasing function. What was the right-hand approximation?
13.
Ooh, that's pretty far off. What was the left-hand approximation? That was jutting out or over. 22, that was pretty off. What was the midpoint approximation? Ooh, so who's better, trapezoid or midpoint on this example? Midpoint. So they're both good. They're both good. There's no time where you're going to have to choose which one to use. It'll be stated in the question whether to do a left or a right or a midpoint or a trapezoidal. Or it'll say something like, put the following in order as far as what are the lower approximations and the higher approximations, etc. But anyway, trapezoidal is a good one. It is close, but it does make sense that it's going to be a little bit below the actual. Now, I think we ran out of time this day. Period 1 did not. I showed you guys another example, which was similar, but let me show you one more time where we're going eventually. Because didn't we start off chapter 4 with just anti-deriving stuff? Integration, basic integration formula. But all of those integrals were, what's that word to say no bounds? Indefinite. All those integrals were indefinite. What are we dealing with now? Definite. Definite ones have a beginning, have an ending, have an area. Indefinite ones have an antiderivative. Well, they're both integrals, so where's the tie-in? Well, guys, what's this problem again? The integral from 0 to 3 of 9 minus x squared. Did we do this one? We did. Justin, you and I talked about it, but that was after class. How would you antiderive this guy? Ignore the bounds. How would you antiderive this? 9x minus 1/3 x cubed. Now we know the answer to this is 18, so how on earth can this get me to 18? Now there should be a plus c, right?
Yeah.
Okay. I'm not teaching you why, I'm showing you how. There's a very big difference in the whys coming in the next section, but I'm not showing you why, I'm teaching you how. And those two numbers, they're x values, right? How do we know they're x values? Well, they're x equal values that cut the area, true? Okay, so they're x's. Well, do I have a place where x's should go?
Yes.
But I had two different x's. Do you think I can plug them in at the same time?
No,
Different times. So, I'm not going to tell you why, I'm just showing you how. Plugging in the top one first, because you have to. Plugging in the top one first, because you have to. I'm not telling you why, showing you how. Plugging in 1/3 times 3 cubed, plus, well, c is not x, so whatever, plus c. Plugging in the top one, minus plugging in the bottom one, 9 times 0 minus 1/3 times 0 cubed plus c. What happens? What happens to the c's? They cancel. Which is why, for definite integrals, we're going to stop writing c's because they always cancel when we subtract. Indefinite, we need it. Definite, it doesn't really make a difference. They cancel out. Okay. What's all this stuff? 0. 0. What's this guy? 27 minus 9.
18.
What did your calculator say the definite integral was? Snap doggy dog.
Hold it up. You do it on this
Snap
one.
doggy dog. Oh, you can hit the map button. So you can scroll over this way faster. Function integrate. Or you can use your cool little shortcut.
I'll get some scotch tape.
Indefinite. Ooh, guys, good question. How can you tell whether something is indefinite or definite?
When it has
Oh, motion packet.
Oh, here we go.
Motion packet. I believe there's a question for this on motion packet. How do you know, come back to this in our notes, don't worry. How do you know whether something is indefinite or definite. Let's start on worksheet number 4.
Wait, see, I have a question.
Worksheet number 4, motion packet. Was about the
When you gave us an example, like you could ask us, like they could tell you, like put them in like increasing order, go left, right.
Yeah.
But can we just always assume right's going to be the smallest and left? No. So we have to find all 4 of them then.
if the function is decreasing, the right will always be under.
Okay.
The left will always be over. But what if my function is increasing? The right will be over. The left will be under. It all depends on the increasing or decreasing nature of your function.
But then, like, what would we actually, like, because we know that, like, knowing that, like, increasing, decreasing, like, or where.
Then you can say the right will always be the lowest, the left will always be the highest. Midpoint and trapezoidal, you might have to consider the curvature a little bit closer to know which one's which.
Okay.
But you would know that the area, well, you know the trapezoidal is under of decreasing because it's going to connect and leave off curvature. You're going to know that the midpoint, let's just save that one for later. And you're going to know the actual area as far as, well, he's greater than the under and he's less than the over. Because they might have you put the A for the actual area. Okay, motion packet. Speed is the absolute value of, yay, we know this one. Plug it in. Plug it in, sorry, write it down. Velocity. Number 2, if the velocity and acceleration have the same sign, both positive or both negative, aka velocity is negative and decreasing, speed is increasing. Decreasing, acceleration is negative too if velocity is negative and decreasing, or if velocity is positive and increasing are the only times where speed will be increasing. Speed is always positive. No, it's an easy mistake. Remember, positive and increasing have 2 very different meanings.
Yes.
So speeding up, speed increasing. If the velocity and acceleration are opposite or different, so yeah, I would say opposite too. Opposite in sign. Then speed is decreasing, aka slowing down. Aka, wait, listen. Your brain's not going to like it. Remember that quiz we took? Okay. If velocity is positive, headed that way, and decreasing, okay, slowing down. Or if velocity is negative and increasing. That's also slowing down. You're trying to go that way. The acceleration is, in a sense, pulling you back the other way. So that would be another time when you're slowing down. Okay, but why I had you look at this page. Have you guys already found it? What's number 4 say? The difference between number 4 and 5. Alright, Riley, here we go. Or Riley. Goodness, I was just looking at Riley. What was the answer? That was true. 4 and 5. 4 and 5. 4 is indefinite. 4 is. I can tell you're getting there. 4 is indefinite. 4 is indefinite. And number 5 is definite. So let's look at the differences between these two. Number 4 is indefinite. And number 5 is definite. Number 4, an indefinite integral will always give you an expression for. Now, I would say in general, for any indefinite integral of f of x dx, it will give you an expression for the antiderivative at at x. But in this specific case, if I am integrating velocity, what am I getting specifically? The antiderivative who is what? Position. So I'll be getting the position function x of t, right? I'll be getting the position function at time t. But if it was a general integral of f, it's like, okay, fine, I'm getting his antiderivative, whoever he is. Don't forget that you will have a plus c. Good, the constant of integration. You're going to have a plus c for an indefinite integral. Because we don't know if the antiderivative had a constant or not. The value of which can be determined if you know a position value at a particular time, right? If you know a clue. If you know some sort of x and some sort of y, or in this case, some sort of t and some sort of position, time and position, then you can plug in and find c. Okay? I mean, related rates is based on time, so in that way they're kind of all related and you have derivatives, but not specific. The clue is like, hey, there's something extra to plug in, do it. That's what's going on. Number 5, definite integral. So the answer will be a value.
Yay.
It's going to be a value. It's not going to be a function. It's going to be a value. You're finding an actual area, an actual number. So it's going to be a number. It's going to be a value. I like that instead because if they don't necessarily give you all the clues, you might have some sort of variable standing for the value. The number represents the change in, now hold on. In general, I would say the change in the antiderivative. This was just f, but since it's velocity, remember that one problem we had in the motion packet earlier on? I was like, hey, guess what? Not only is it moving right for this region where the velocity is above, but it's moving right how much? And I said, the area is how right it moves, is how much it moves right. And then when it went below the axis, when the velocity went below the axis, negative velocity, my object was moving to the left. So it was moving right, moving right, moving right. How much? I don't know, whatever the area ended up being. It was geometric, you could have found it with geometry. What? Coming back. Then it starts moving left. How much? The area under. What number was that we were looking at? It was the one with the graph. Is it worksheet number 2, example 2? Worksheet number 2, example 2. Do you guys see that graph of velocity with the little pointy, like, if you were to shade from, is it 0 to 5, where the object was moving right, because the area is positive? Yeah. If you were to shade that, okay, it's not really a trapezoid or a triangle, but it's a rectangle plus a triangle, kind of.
Yeah.
You see how we can kind of like draw lines and figure out what the area is with rectangles and triangles? So you could actually find that area and say, that's how much right it moved during 0 to 5, first 5 seconds. And then from 5 to, what was the end, 9? From 5 to 9, that's a trapezoid or a triangle and a rectangle. We could find that area and say, that's how far it moved left. We could even ask us something like, if the particle started at the origin, started at, I don't know, position equals 0, did it ever return to the origin from 0 to 9? Well, looking at that graph, what do you guys think? Did it ever return to the origin? No. Because can't you tell just by looking at that the area, the positive area from 0 to 5 is greater than the negative area from 5 to 9? So did it ever get back? It went farther to the right than it went to the left. So you'd be able to answer and say, no, the object will never return to the origin between 0 and 9 because the integral from 0 to 5 was positive this much, the integral from 5 to 9 was negative this much, and so the overall displacement is here, and it never returned. Or you could say it moved farther right than it did left. It never returned. Okay, back to the definite integral stuff. So, represents the change in, how would you answer it? Position. Wait, the change in position. Change in position, there's a snazzy physics term for the change in position. The final minus the initial, where you ended minus where you began. What's that snazzy physics term? Displacement. Displacement. And isn't displacement just x of t2 minus x of t1? What did I do up here? I anti-derived. This could be velocity, this could be position. And then I said position at time 2 minus position at time 1. That's how you solve a definite integral. By the fundamental theorem of calculus, yes, that's section 4.4. We're getting there. That's the y. Since velocity is position prime, the integral will yield the antiderivative of b, or of time 2, minus the antiderivative of a. This is also known as, oh, it's right there, displacement. The answer can be positive, or you guys just logically would fill in what? Even if you didn't have a clue. Yeah, fill in negative. The answer can be positive or negative depending upon if the particle, come on,
Right.
lands to the right or to the left. Right?
Right.
Correct? Because if it lands to the right, isn't that positive displacement?
Right.
If it lands to the left, that's negative displacement. Good. Of its original starting position. You're having way too much fun with that. Number 6! Whoa! What's number 6? It's a definite integral from time 1 to time 2 of who's the absolute value of velocity?
Speed.
Speed. So I'm thinking an integral of speed and not velocity. It's like I don't care about whether it's moving to the right or left. It's like I don't care if the displacement is to the right or left. It's like I'm caring not about displacement, but about total distance traveled. Ooh, snap! Is also a definite integral. And so the answer will be a number. Oh, well, they said number. I like value better. The number represents the total distance. But you're right. The total distance traveled. I know there's only one blank. It's misleading. Maybe on purpose. The total distance traveled by the particle over the time interval. The answer should always be
Positive.
just like speed. Positive. And think about it graphically. You guys had to answer this when you were doing speed increasing, decreasing. Question. Think about what's inside the integral, the integrand. This function, if there's absolute value bars outside the function, what's true about that graph? It's always above. So whatever was above the x-axis stayed above, and whatever was below went above. So all the area is going to be positive, no negative, and you're just accumulating, adding it all up, like your odometer would. Maggie?
For 4.3, is that we can use this method instead of using our
No. E for effort. And the reason is the following, because on the AP, when they ask you for, you guys can start writing, when they ask you for a left approximation, a right approximation, a probability approximation, A, they're almost never giving you a function, which means you can't solve it by hand anyway. And B, even if they do give you a function, the correct answer is going to be wrong. Does that make sense? Yeah. Close the answer. So, integral definition. Let's talk about a definite. Does that make sense, Brad? A definite integral. There's a number down below, there's a number up above. It has a beginning and an ending, and a finite area is the answer, which we could call a number or a value. Oh, it's missing something. Sorry, this needs a little N up here. Not red though. Black, please. This is the integral, the definite integral from a to b of the function f of x dx is equal to, one way of writing it is the limit as n approaches infinity. This is a little I. They could use an I, they could use a k. The book or even the AP usually uses an I. I think pre-cal like to use a k. Anyway, the sum from 1 to n of heights at certain values in between partitions and delta x's of the certain partitions. The I just means, hey, for the first, second, third, fourth, fifth of each of the little sections that we're adding together in a set interval from A to B. Another way of writing it is, I write too fast in this. Silliness. There we go. The limit. When you see the double lines in this little triangle, double lines approaching 0, this is a snazzy way. Think delta changing. I guess in a sense they could have said delta x. They don't like doing that though because the delta x's don't have to be equally spaced for this to be true. So this little double line thing, you guys have seen it before when we talked about magnitude of vectors last year. We had the little double lines. Just think this is the space or the section of the subintervals. The snazzy word is partition. When we partition the A to B up, these partitions, when you fit more and more and more and more, as n goes to infinity, you have more and more infinitely, well, approaching infinity, many rectangles under that curve. And so the partitions, the bases are going to approach 0. That's what's going on with this notation, but ultimately it's the same idea. So when you guys see these little C's, if you see these little C's in homework, they're talking about the special x values. They're talking about the special x values for each partition as far as, hey, what are you plugging in? Is it the left? Is it the right? Is it the midpoint? The C sub I says, I don't care, it's somebody. In words, we can almost use technically what's on the screen before that I don't think we wrote down. So in words, we could kind of use the idea is as the number of rectangles increase, as we partition A to B, more and more as we partition it, more and more, partition it higher and higher. I don't know the right word to use. As we partition it. Anyway. As we fit in more and more rectangles, as n approaches infinity, as the number of rectangles fit in between A to B, so will the accuracy. And the approximations will approach the actual. They will stabilize, they will converge. So, in words, we could say the actual, let me say the definite. That's not going to work because my smartboard's not working. Okay. Half working. The definite integral from x equals a to x equals b of f of x is the limit as the partitions approach 0 of the Riemann approximations. We'll put it that way. And technically, guys, this could work for if you're doing the left or the right or the midpoint or the trapezoidal. But technically, out of all of them, the Wright's formula is the easiest. The Wright's formula is the easiest. I think I left off the N. Anyway. So that's why technically this one is showing the right because you're already starting one removed from A. It would be C sub I minus 1 if you were starting from the left, because then you would be starting at the far left and not one removed. But anyway, that's all super technical. That's more necessary for BC than for you guys as far as understanding the limit definition. To end class today, we're not going to solve this the long drawn-out way. We could. It'd be pretty messy, but we could. I'd have to teach you a couple formulas having to do with summations. Maybe I'll try to show you one tomorrow. I think I've been saying that for a while. But we finally get up to the actual definition itself. First of all, we do need to label this because this is forever number 33. Yeah, the definite integral. So definite integral from a to b of f of x of the function is the limit as, I use this one, as the partitions approach 0, so as we get infinitesimally thin partitions, as the partitions approach 0 of the Riemann approximations. Another way of saying it is as n approaches infinity, or as the number of rectangles approach infinity of our Riemann approximations. I think it's 33. Anybody double check me?
Yeah. Yes.
Okay. So the crazy thing is down below, change from a Riemann sum to an integral. The hard thing is, looking at this function, guys, I have no idea what a and b is. If you notice, a and b is not present yet. It will be present eventually if we were to actually solve this by hand and have to actually plug into our function and show where to start and where to end. But currently, the really, really general form of it, a and b is not present. So we're going to go ahead and keep it indefinite for now, just because without extra information, maybe they'll give you a graph and tell you a to b, maybe they'll state it. All we can say is the integral itself as far as the indefinite, but this is all like, hey, yeah, guess what, integral. This little delta x becomes a dx. Then all I have to remember is this little c sub I are just special x's that got plugged in. So they got plugged into, well, who was the function if the c sub i's got plugged into the x spots? 6x times 4 minus x squared. That's it. They're not asking you to solve it, they're just asking you to realize, hey, this notation really is talking about that integral. Give me more information if you want me to actually solve it from a to b. So what would you guys fill in for letter b? The integral of 3 over x squared dx. If they want me to know a and b, they better give me some more information. I would say stick it to the man. Unless they give us more. So that's how you use the integral definition, just to take something that's written really nastily, in the sense of that long limit definition of an integral that we haven't quite seen how it actually works. And once again, it's not really even an AP skill that we need to develop. But just how to take this and say, oh, hey, that's really just the integral and how to solve it the longhand way. And by the way, this whole antiderivative thing, I think it's going to help me soon solve it the by-hand way. Kiddos, how would you write an integral to solve these ones if they said, hey, here's a graph, here's a function, here's the area I want to find. How could an integral do this for me? What would you guys answer for the first one? Of? From 0 to 2, because everything is in terms of x, of the function 4 minus 2x. If the bell rings, give me one more second. How would we solve this one?
You have 5 minutes.
Oh, duh, it's triple. I thought it was 53. It's already past 53. Anyway, go team. 0 to 2. Oh, why? Nice. You guys get it?
No.
This one, everything was in terms of x. So if I'm going to plug that function in terms of x, I need the dx, which means these need to be x bounds. So I use the x's to cut. If I want to put a function in terms of y in, I definitely can. That's not against the rules. I just need to make sure everything is, including the bounds, in terms of y instead. You see it now? Make sure everything is in terms of y instead. So some of homework in section 4.3 is literally just being like, hey, you get the notation-y stuff? Like, can you actually write an integral to solve for what we want you to solve for? Or can you take something that's written as a definition and rewrite it as an integral that you're going to learn these antiderivative ways of solving, et cetera, et cetera. So that's pretty snazzy. What would you guys say for this one, though, for number 3? Ooh, using geometry. They're not even letting us use that whole antiderivative thing. How do we solve this guy? We kind of saw something super, super similar yesterday. Yeah, go with 4, because this is a y equals 4 function, right?
Yeah.
F of x equals 4. So we graph that. Isn't that just a constant? Pretend that's a constant. So y equals 4. But how do I? Where am I? Oh, just put it?
Yeah.
Okay, and then? Okay, and then? What shape is it? Okay, so rectangle has an area formula of base times height. So how do I apply that in terms of what I have here?
2a. 4. Wait, 2a. 2a.
No, 4 times.
4 times a or 2a?
2a.
Because my base would be, right? A to the right and a to the left. And what's my height going to be? Nice. So my final expression, it's not a number, but it represents one, hence why I would call the value. But either way, 8a. How about letter B? Ready, set, you guys in your groups, play with it. Go. It's a transformation of a basic graph.
Oh, so sad.
I just like skip the chocolate and then go catch up.
It's okay, just work on the example. Have someone else write what you're saying. What's the graph look like?
Shifted down.
Yeah. It's shifted. Yeah, two triangles. Oh, wait, wouldn't it be flipped?
Yeah.
It would be like this, it's this one on the bottom maybe? Hey.
Yeah.
But I don't feel like that would change, you know? Yeah. I'll find out. Yeah. Yes, I'll find out.
Alright.
Golly.
I don't know what it's on zero order. first order assembly. Yeah. And then
What are you talking about?
What's the graph look like?
Upside down.
It's an upside down V because the negative flips it vertically, the A shifts it up. It's going to be a with A right here, right? Where does it hit here and here though? That's kind of important. Set y equal to 0. Y is going to be 0 when this guy is equal to A, which is going to happen at negative A and at positive A. Area formula for a triangle is just area equals 1/2 base times height. So what's the base?
2A.
2A. And what's the height? A. So what's my final area? What do you guys think?
Not too shabby.
Actually, go ahead.
So is area always positive?
When it is above the x-axis, yes. When it is below the x-axis, the area is positive, but we establish it as a negative because it represents negative displacement or negative change.
So if you have like a function, like a graph, trying to get the full area, but it's not positive.
But remember, it's defined to be the area between. So we didn't go below because the area between was right there from the bounds. But if it did go below, we have to take this minus that.
Okay.
All right, good job, cool kids. I'm going to stop the recording because I need to set up next period.